Welcome to this video. We're going to go over how to complete our CPU for the class. So we're going to merge the data path and the control unit together. And if you noticed in the previous video, we already did step 1 and 2 right here, where we copied and pasted the control unit onto the same circuit as our data path. So next is step 3, which is replace the switches in our data path by the tunnel that connects it to the control unit's control signal. So let's do that. So I now have my real sync buttons connected up to my control unit. I'm just going to do one more quick test. So I'm going to enable my ticks, up the frequency maybe a little bit. If I hold down start, and then let go, I get the 1 clock cycle start signal that starts my my control unit. So everything seems to be working. And if you notice, I kind of moved all my controls into one little spot. That'll help us as we debug right there. So the next step is to connect these control signals to our data path. So we can go ahead and stop our control unit by just resetting it. Should be back into TSC, and we can even turn off our ticks as we go and edit. It is, by the way, if you just open up your circuit, it's a good idea to just shut off your reset by turning it to a high voltage, and then click the clock a couple of times as well. Also, I didn't tell you in the previous video, make sure that your clear has a NOT gate on your D flip-flop so that when the voltage is high, it's not resetting your state machine and keeping it in the first state. So let's go ahead, and you can either copy and paste these tunnels, or you can remember what they're called. So we'll copy subtract over here. And we got our subtract switch right here. So we just delete the switch and we replace it with the tunnel. Just like that. So we're going to do that for all of these inputs, so you can do that. And then we also have some other control signals right here, like PC to bus 1. Well, hopefully you remember what that is from your data path lab, PC to bus 1. So we delete that switch. We add a new tunnel in our wiring. And just do PC to bus 1. And make sure you spell it the right way. A good way to check is what color the wire turns, so PC to B1 right there. And you can see that my wire is blue. That's a good hint that I didn't spell that right. And so now we connected up PC to bus 1. There'll also be a switch for MBR to bus 1, MEM to MBR, bus 3 to MBR right here, bus 3 to MAR. And then you're going to have switches for here. You're going to have the signed immediate to bus 2, this unsigned immediate to bus 2, the upper immediate to bus 1, the target to bus 1. You can have those switches. You're going to have the switch bus 3 to IR as well. And then 1 to bus 2. Now the one switches that you might see are missing are the switches that for your registers. There's no bus 3 to register 0, no bus 3 to register 1 or 0. There is a bus 3 to register 2, but you don't want to connect that directly up. We're going to have to do some more work to connect up these switches. So that's what we'll talk about next. So you can see right here on step 4, it talks about this in a little bit more detail right here. So I will show you exactly what this is talking about. So in your library, you should have a 2x4 decoder. And a decoder is something that turns a binary number into a signal. So go ahead and drag one of those out and place it down, and I'll connect some switches up to this so we can see what this guy does. So I got two switches here. There is an enable. Now this one is, you got to be really careful. The blue wire is on the other side of that, so I always like to drag the wire away from the chip to make sure I really get that. And just connect that up to one switch right there. And then we connect the S up to another switch, and we're going to get an error because this is actually two wires. So just take my switch and make it two switches. All right. So this circle here, of course, means it's low asserted. So when it's a 1, it's off. And if we notice the little circles on this side, and again, make sure you drag the wire away from it. To make sure you really get the wire. Sometimes people pull a wire to it and they place it here, but they don't quite connect it to the dot that's on the line right here. All right, so it's off, and you notice all of these are off as well. Low asserted, right? So on means off in this case right here. So this is off, all of these are off. All right, when I turn this one on, notice that this wire turned on as well. Again, low asserted, so low voltage means on. So that one's on. Now this right here, if we look at it as a binary number, that's 0, 0, so we have wire 0 is on. If I do 0, 1, then that wire 1 turns on. If I do 3, notice wire 3 turns on. And of course 2, we see that wire 2 turns on. So the decoder looks at the number on its input, it converts it, it knows it's a binary number, there's two wires there, it converts it to a binary number and turns on that number. And if you notice, we have 4 registers here. So what the control unit's going to do, it's not going to tell us to take register 3 and put it onto bus 1, or register 3 and put it onto bus 2. It's going to just say, let's put register S onto bus 1. So this guy right here, the control unit will come and turn on this guy right here. This guy right here will go look at our instruction register right here. And it will look at what register S is, and then it will decode that and turn on the real register that we need to do. So I'm going to do a little work off camera and get this set up to show you what your circuit should look like. Now if you notice, there are two control signals for bus 3. Bus 3 to GPRD and bus 3 to GPRT. Just ignore this one for now, we'll get back to them. But we got these two here. For bus 2, besides the 1 to bus 2 on these, if we look at that, we have GPRT to bus 2 and GPRS to bus 2. So there's two control signals for bus 2. And there are also two control signals for bus 1, GPRS to bus 1 and GPRT to bus 1. So each bus, bus 1, bus 2, and bus 3, have two control signals that control the registers that get put on there. There are other control signals like our signed immediates and other stuff, the 1 to bus 2, the PC, the bus 3 to MAR. But for our registers, each bus has two control signals. So what I've done is for now I put switches on these so we can see how this works without actually running through our control unit. But eventually those will connect up to our control unit. So we have one switch, bus 3 to GPRT, and another switch, bus 3 to GPRD. Now both of these things will want to turn on a clock for, since it's bus 3, it controls the clock. But both of these things will want to turn on bus 3 to a register. So in order for both of them to work together, we're going to AND their outputs together. If you notice, I have register 0, or the 0 wire coming into an AND gate from this guy, and the 0 wire from this guy coming into this AND gate right here. Okay. And I wanted to show you this before all the wires started getting crossed up and confusing. So if we notice 1 right here connects up to this AND gate, so we're going to grab 1 and be really careful not to cross our wires. So I find it easier to draw a straight line, stop, and then drag and draw another straight line. So now we got 1 and 1 connected up to this guy. This guy right here, he's going to be 2 and 2. And this guy down here, he's going to be 3 and 3. Now you might not have enough space for all of this in between your control unit and your data path. That's okay. Just use tunnels and put it somewhere else. Like maybe you can put it down below the control unit. All right, so now we're going to take 2 from here, and he's going to connect up to this guy right here and pull him a little further out. And then we got 3 connected up to him, so we're going to connect this 3 down here. And it's okay to cross wires, but if you don't want to end it, if you get a little circle right there, then you know that you connected those 2 wires. But it's okay to cross them as long as you completely cross them. You don't stop here and then start here and there, because then you connect those 2 wires. So if your wires turn red, then you probably crossed them. So the control unit will not turn on both of these switches at the same time. It'll only turn on one. But let's say the control unit decides bus 3 to GPRD should turn on. So this switch will turn on, and you can see that this turned on, and as it passes through the AND gate, it turns on that way too. So, and if this one wants to turn it on, then it will turn it on, and then you see it through the AND gate, it turns it on as well. Okay, so now what do we hook this part up to? Now this part, they're not going to be switches, they're going to spy on our instruction register to see what instruction is in there. So we, if you notice, I turned this one on, notice it's 0, 0, so register 0 is turning on. If I change it to 2, that's 2 in binary, you see that register 2 turns on down here. And I'll just pull that wire out so you can see that it's a low voltage, which means on. So we just need to connect these up to our instruction register, but there are only 2 wires, and our instruction register is 16 wires, has 16 wires, and this only has 2. So going back to our programmer's reference right here that we have been looking at quite a bit, we'll click on the add, and if you notice, we have RT, RD, and RS right here in each of these spots. So D is in 6 and 7, 8 is, or RT is in bits 8 and 9, and RS is in bits 10 and 11. Let's scroll down to the next instruction. S is still in 10, 11, and RT is still in 8 and 9. And in fact, if you look at every instruction, RS is always on bits 10 and 11, RT is always at bits 8 and 9, and RD is always on bits 6 and 7. So again, S, 10 and 11, and then 8 and 9. Now, they might not always be there, but if they are there, they'll use these 2 bits. So what we want to do is we want to grab this wire here, and make sure you grab it from the Q output from your instruction register. So when the instruction gets clocked into the register, the voltages will be on this wire. And go up and grab a splitter. Right there. And make sure the bit width is compatible, so 16 wires. We're going to fan this out 3 ways, and so RD, if you remember, is on bits 6 and 7. So I'm going to say bits 6 and 7, I'm going to put them on the 0 on the right part, and I'm going to shut all the other ones off. So the ones that are not register bits, RS, RT, or RD, will just shut off right there. So you notice now on over here, if we zoom in a little more, maybe we can see it a little bit better. We got bits 6 and 7 right there. And We'll do 8 and 9 is RT, so they'll be on 1, and then 10 and 11 are RS are in bits 10 and 11, so they'll be on 2. So we got bit 6 and 7 on the right side, bit 8 and 9 in the middle, and bit 10 and 11 on the left side. And we'll go ahead and shut off all the rest of them so we got each one of those. And then so we don't have to drag wires too far, we'll probably grab a tunnel here and just label our bits right here. So this one is RD, bits 6 and 7 are RD. Another tunnel for our RT right here. And a third tunnel for bits, the RS bits. Okay. So now we see we got the RS bits on one wire, the RT bits on another wire, and the RD bits on another wire. So you notice this is called bus 3 to GPRT, so this should look at the T bits. So we'll just replace him with a tunnel. And say RT right there. Now this is the D bits, so we'll replace this one with RD. And now when the control unit decides to turn on this guy right here, it's off right now. When he turns them on, this guy's looking at the instruction. Our decoder decodes what register that instruction uses and turns that one on. If the control unit decides to do this one right here, then it will turn that one on. So I deleted my switch on the clock on this register that was named bus 3 to register 0, and I replaced it with a tunnel, bus 3 to register 0. When you name the tunnels, just make sure you don't accidentally name it the same as this control signal. We're going to get back to him. So I'm using a little bit different format. It's bus 3 to R0. I won't have to worry about conflicting with that. So up here we have register 0 is this AND gate right here. And just grab a tunnel and connect those two up. And now if the control unit wants RT bus to turn on that control signal, he'll turn on him. Our decoder, looking at our instruction register, figures out exactly what register that is and turns on that register right there. And so you'll need to connect this up to register 1, bus 3 to register 1, bus 3 to register 2, and bus 3 to register 3. And you're going to have to do 2 more of these circuits as well for bus 1 and bus 2. So we got all of our GPR numbers to bus 1, and then we also have all the ones to bus 2. So you're going to have to create 3 of these right here, and they're going to connect to so we created one. The one for bus 2 will connect to all the bus 2 switches, and then you'll create one for bus 1 that will connect to all the bus 1 switches. And then looking over here at our control signals, you have GPRT to bus 2 and GPRS to bus 2. So this looks at the S bits and connects to the enables on the tri-state buffer for bus 2. And these look at the T bits. They both go into the AND gate just like we did for bus 3. And we'll also do that for bus 1. We have GPRS to bus 1 and GPRT to bus 1 that will control all the switches for our registers to bus 1. Just make sure when it says S that we look at the RS bits, and when it says T we look at the RT bits. All right, finally what do we do about this lone guy right here? Well, this lone guy is actually for our jump and link instruction. And our jump and link, we don't put a register in the instruction. It just always uses register 2. So now there's 3 things to turn on for register 2. We have this guy that could turn on register 2, bus 3 to register 2, this guy that can turn on bus 3 to register 2, and that lone control signal right here all by himself. He can turn it on too. So we take the register 2, and again, this is only going to be for bus 3. We take this AND gate that controls register 2, and we just give them one more input right here. And we'll give them 3 inputs. That gives us another wire right here. And go ahead and copy that tunnel. As you drag down, just make sure you don't accidentally connect the wire part of that to a wire that you don't intend to, and we can connect that all up. So now the control unit can either turn on this guy, or this guy to control register 2. So we need to make another one of those for bus 1, another one for bus 2, and then we got all of our registers connected up. Now the one for bus 1 and bus 2, they're not going to have this this guy right here. They'll just be like all of these AND gates will only have the 2 inputs. It's only on bus 3 that we have this lone control signal getting ANDed in there as well. Okay, so there are only a few remaining switches to hook up. Right hooks up to our memory, and find my memory up here. Here's right, so we just delete that switch. Make sure we keep that NOT gate in place. We also have our input to bus 1, and that's going to connect to input. The only problem is the control unit thinks this guy is high asserted, unlike all the other tri-state buffers, but he's really low asserted. And the reason for that is it's also meant to power a light. So you want the light to turn on when you want the input. So we better put a NOT gate on this guy right here for input, or else he'll be on when he's supposed to be off, and off when he's supposed to be on. That'll cause all sorts of conflicts in our data path. The output, you can just connect that to a light, or if you want to get fancy, you can have an output register that gets its input from bus 3 and have that the output connect to that. And it'll actually work either way, with a NOT gate or without a NOT gate, but on the clock. The air right here, you can just connect to a light. This connects to the mux right here on our memory, the MBR, mem to MBR. And there is a couple more things that we need to connect up. Our control unit's looking at this pretend IR register right here. You probably want to delete that and connect that up to our real IR register over here. And just grab it. You can either grab a tunnel or you can drag the wire. Make sure it connects to the Q bits of the output of the IR register. And make it 16. Name it IR. Now you might have already have a tunnel in there that might be conflicting, so just make sure it's connected up, and you might already have a tunnel named IR that would conflict. Make sure it's just connected up to the right spot. Okay, and I think that is all of the switches that you need to connect up. We talked about all of them. So you have 3 of these circuits, right, that we just made. The other 2 do not have this guy right here. One of them controls bus 1, the other controls bus 2, and this guy controls bus 3. So I just talked about step 5 right here. Now we're on to step 6. We got the 0 and the sign, and this is to help the control unit know if we want to take a branch or not. So we have the branch greater than 0, branch less than 0, branch on equal, branch on not equal. And they need some information from the ALU to know whether they should take the branch or not. Now, if you remember back to your ALU lab, you created this 0 output. Now's your time to cross your fingers and hope it works right. But just put a tunnel on there and connect it up, call it 0. And we have this switch right here that was pretending to be the 0, so we'll probably delete that. Okay, now we also need to hook up the sign bit, and a lot of people make this mistake to think that the carry out is the sign of our what's on bus 3. It's not. This is just for debug purposes, so it doesn't connect anywhere. What is the sign? Well, it's the most significant bit of our bus 3. If it's a 0, then our number is positive. And if it's a 1, then our number is negative. So just connect a splitter up to that 16 bits wide. And we can actually just fan this out one time if we want, and we can shut off everything but bit 15. And then we'll have one wire that's our sign bit as well. So now we left bit 15 on, and so we can again grab a tunnel and tunnel that over to our sign. And I might have left one of these bits on. Yep, bit 0. There we go. And now we tunnel that over to our sign, of course. Delete the switch that was pretending to be the sign. And now our control unit can get information from our ALU and know if our number is 0, positive, or negative. Okay, next we want a control area where we can see everything that's going on. And this will really help when we debug. We don't want to have to be scrolling around and looking what's inside of all of our registers here and everywhere. So the best thing that we can do is just grab tunnels and make sure you're grabbing them from the Q output right here. So the Q output of the MBR, the Q output of the MAR, the Q output of our PC counter. Of course, our instruction register, we already have a tunnel named IR. Register 0, 1, 2, and 3 right there. And put them all in one area so we can see everything. I've also grabbed my clock, my clear, my start, and my data. I've tunneled them over. And lastly, I got my micro address that we saw in the control unit. And you just connect that up to right here. See where this little display connects up to this wire right here. You can connect up your micro address, so we can see everything that's going on. Now, once again, if you first open up your lab, it's important to shut off your reset and then go ahead and clock a couple of times. That'll get rid of any error messages. What it does is it clocks the micro MBR, which sets the control signals to all off that when we're in our halt state. So now we just need to load a program into our memory. We're going to skip the loader part. That way we don't really have a way to read from files. So we're just going to take one of our programs and convert it to a hex file that we can put into our memory and run it. Just a little warning, I deleted the labels in my, the start and the data labels in my control unit. You might want to not delete those labels just so you remember where they came from. But notice right here it just feeds directly into our circuit. Actually, this guy doesn't, so I have to find the other one. But what will happen is this is the switch, and this is the output of my state machine, and they might conflict at times. So I better find out where data connects to and fix that. And that's right here. So we'll just connect that directly, and then we'll delete those two tunnels. That way the data is my switch, and then the output of my state machine connects directly into my circuit. So you can do that, or you can leave the start and the data tunnels there and just label this data switch and start switch when you tunnel them over to your control area. That way your input to your state machine does not connect to the output of your state machine. That would be bad, and things wouldn't work that way. So in our files section right on Canvas, we have a bin to memory class. Go ahead and download that. And if you get any warnings about this being potentially dangerous to your machine, just say, I understand the risks, and keep going. So I'm going to download that and put it on my desktop with the rest of my files. Now you'll want to do this with one of your own programs, that maybe you'll get more satisfaction of running the program you wrote on the computer you made. So this is what I wrote in class with you guys, the loop.tsc. So I'm going to download him as well and put him on the desktop. Now in my assembler, I opened up that file. So if you don't remember how to start the assembler, it's just Java TSC assembler, and that will open up your assembler. You can download the assembler from Canvas. And we have this file here, and if you remember, this button right here turns it into a binary file. Make sure it says creating whatever your name of your file is .bin, and that means you should now have a binary file in the same folder as your .tsc file, and I put that on my desktop. So I have that Java class that I did, the bin to mem class on my desktop, and I also have my loop.tsc on the desktop, and I also have my loop.bin file. So I'm in my desktop folder now, so I can run Java bin to mem, and then I include my loop.bin file as one input, and then the name of the output file. So I'm going to call my output file loop.txt. Okay, and we should see it convert this, and now you should have a loop.txt file on the desktop. Now that loop.txt file will be in the right format, so we just go and find our memory. We right click on our memory and we load an image. Back on our desktop, we have the loop.txt on file that just made, and we can see that our instructions for that program are now loaded up in memory. And we can even see our first instruction is coming out of the memory because we have a 0000 in our memory address register, so memory's looking them up, and he is spitting out our first instruction. So back to our control panel right here, where we can see everything that's going on. Make sure you reset it. We can go ahead and let our clocks go. This is where you want to cross your fingers and hope everything works. Most likely it's not going to. You'll have to do a little bit debugging, which I'll include after you see this working. So we enable our ticks. If you want, you can make it go as fast as possible. Depending on your Java version that's running Logisim, this might be it might be really fast or really slow. And then we go ahead and we click our start button. We release, and we can see it's working. We can see it go through. Look at our registers changing values. Look at our program counter go. We can tell it's kind of going in a loop right here. And we just kind of patiently wait this out. And our output light turned on. And we can see we're in state 6E right here. And we got the output on bus 3, 48. We can look at our output register right here. We see that 48 is our output. We can acknowledge that. And then we go to 2C. So what you need to do to pass this off is 1, submit your file to Canvas, and 2, make a video, show your entire circuit in the video. You don't really have to explain much. You can explain, just show your entire circuit. You don't really have to explain much. Then show you loading a program into your memory. Go to your control panel here and run your program and show that you get the same output that the TSC simulator will get. So next I will show you when things go wrong, what do you do? So I have loaded my loader from a ROM, and we can see that at the end of the memory. It's just a quick review on how to use your simulator. I click Load PC. Now I'm going to select my input file. From my desktop, the loop.bin file. And I'm going to click Start, and that will load my file in here. So when you're going to pass off, first you should use a program that you wrote, and then you show your program running in this simulator right here. And go ahead and let's not clear our registers, we'll just clear our trace. And so we got everything cleared out, and we'll clear our registers. That's fine. Now our program counter's pointing to there, and we can just click Start, and we can see that we have 48 on our output. We even have 48 in the register. Now this is 48 in hex, not 48 in binary. And we click our Acknowledge Data, and we're in Halt. Okay. So show that running in the video, and then switch over to your Logisim and run your program in Logisim. And if your simulator and Logisim get the same result, then you have passed, and you can show the video of all that working. And if you don't get the same result, then you have to debug. Now, you can't ask me to debug for you. It takes quite a long time. I'm just going to, as help, I'm going to show you this video on what you need to do to debug, and then it's up to you. In order to do this, you're going to have to understand how all the pieces work. So this is somewhat of a test that either A, you followed the instructions really well and made your circuit work the first time, or B, you understand this well enough on how it works that you can debug it and get it working. You also cannot ask the tutors for help debugging this circuit. The only thing you can do is maybe ask the tutors a specific question or me about the video and what do you mean by this. But you're going to have to do the debugging on your own. So I will show you how to debug. We go ahead and clear all of this up. So we got our registers cleared. We have our program loaded into memory. Then we have this little step counter right here. So we click step 1 time, and we see load high immediate. And now this really didn't do much, but it did put 0 into register 0. Now, before you get too worried about not being able to debug this completely, just look a little bit at this rubric right here. You get 30 points, actually a total of 60 points for connecting everything up correctly. And then if you can convert your program 1 to hex, that's an additional 10 points. So that's 70. And then you get 80 points if you can start your computer. That means it goes to state 50. And an extra 30 points on top of that if you get an instruction out of memory and into the instruction register. It means you complete the 50, 51, 52, those 3 steps that I made you take a quiz on. And then 90 points if your program runs correctly, producing the correct output. Now, if your program runs for a little while, and but doesn't produce the correct output, I will give partial credit on this 90 points right here. So just try to get as much of it as working as possible and get as many partial credit points as you can. So if you remember, step 1 was the load high immediate, and it made sure that register 1 or register 0 got 0. So to debug, you run one step in your simulator and then you run one step in Logisim. So to do that, I am going to disable my ticks. Okay, and let's go ahead and clear all of our registers. Since that doesn't clear our memory, we should still have our program in memory. And that might be step one. Just make sure your memory contents match the memory contents in the simulator. And of course, the loader won't be there, but you can edit your memory contents right here. You can see all of your memory. Make sure that that matches what you have in the simulator. Of course, the loader won't be in your memory in Logisim. So after that matches, then we're going to go ahead and do one step of our fetch, or fetch one instruction and execute that one instruction. We're going to have to do it manually. Now, 2 clicks moves to the next state. So 1 click on this thing, you'll see the new state number, and then the next click turns on the signals for that state. So to get to a new state, it's 2 clicks, and you want to do this really carefully. New state, turn on the signals for that state. Check everything, make sure everything is working the way it's supposed to, then move on to the next state. New state, turn on the signals for that state. Check all of this control panel, make sure you don't see any errors or anything, any red showing up, and then keep going like that. So to get this going, we're going to turn on our start. We click the clock a couple of times. We release the start. Clock again a couple of times. And now we're on 50. Notice it went to 50. Turn on the signals for 50. And so hopefully you know what the fetch sequence is. This is the first step of the fetch sequence. So you can go and you can check to make sure that things are on. Yes, PC to bus 1 is on. Yes, TRA1 is on. Yes, I got memory 0, which is our PC counter, on to bus 3. And then go up here and say, is my bus 3 to MIR on, ready to clock in 0 into the register. All right. Now, if you forget what control signal should be on what state, go to the readings and you have the microprogram control units, so you can open up that. Now you're going to have to convert the 50, which is in hex, to decimal, and that's actually 80. So you'll have to convert from hex to decimal. You can use a calculator to do that. And then you can see, yep, these are the control signals that should be on. Make sure that your data path is doing that. All right. So my data path did this one correctly. Of course, everything's working in mine. Lucky me. And now we're going to move on to this state and make sure everything's happening in that state. This is where it's really nice to have all of this in one spot right here. So again, we click once, we're in state 51. Click one more time. The control signals for state 51 turn on. And so we should be adding 1 to our PC counter. Yes, 1 to bus 2 is on. Yes, PC to bus 1 is on. And we are getting 1 on our bus 3. And yes, my PC counter right here is a low voltage, and we got the 1 coming into it. Yes, it's ready to clock 1 into it. We're also making sure that our instruction, which is 6000, is coming out of memory, going through the mux, and ready to get clocked into my MBR register. This is a low voltage right here. So that's all working. And so go back to our thing. Let's try state 52. We're in state 52, 1 click, 1 more click, the control signals turn on for state 52. So we should make sure, oh yep, MBR got 6000, the instruction, the first instruction, it's going on to bus 1. And we can even see right here, bus 1 says, yep, 6000 is on it. That should be passing through our ALU onto bus 3, so we can check, yep, TRA is on. And we should go up and check our instruction register right here. And we have bus 3 to IR 6000 is ready to get clocked in. So go ahead and if no red shows up and that all looks good, click to state 53. Turn on the control signals for 53. Notice my PC counter did increment. I forgot to show that in the previous step. Our IR, yep, it has our instruction. Okay, so now we just hold tight and hopefully the control unit should do what it's supposed to do. So it jumps to 6, which is the opcode for a load high immediate. We turn on the control signals. Nothing really turns on in this state right here. Go again. So 68, turn on the control signals for state 68. And we should see on bus 1, 0 coming through. The 0 goes through on to bus 3. And if you need to reference that, convert 68 to from hex to decimal. And that's a load high immediate. So we should see upper immediate to bus 1, TRA1, bus 3 to GPRT. So we see here that we have our upper immediate going on to bus 1, which is all zeros. Bus TRA1 passing through, and we get all zeros on bus 3. And then we are making sure that that could go into register 0. So where's my register 0? Up here. Bus 3 to register 0. Yes, we got a low voltage right here. This is what you really want to check well, because that was your 3 decoders circuits that you had to set up. If you messed up anything with that, you might be turning on the wrong register. So that's something to really check. Make sure you got that right register with the low voltage. If something's wrong, then you can fix it right now, and hopefully you can continue. Sometimes you might have to start all over at the beginning and give it another go. That's why it's really important to click really slowly. 1 click to go to the next state, 1 click to turn on the signals for that state. So we see that it's a low voltage right here. We see the zeros coming in. So register 0 should be 0. All right. So we'll click again, 69, turn on the signals for 69. We should see 0 and register 0. Whew. We did that. All right, so we did the first instruction. So now we go back to our simulator. We click step 1 more time, and we got an OR immediate, and register 0 is still 0. So it's still a little hard to debug because nothing's really changing, but our first instruction was to put 0 into register 0. Remember, it's that pseudo instruction that gets split into 2. So then we go back to Logisim, and back here we go ahead and click on our clock. We're back in state 50. Control signals are back on state 50. After we got this fetch sequence working, first of all, that's an additional 30 points right there for getting an instruction out. So you can pat yourself on the back and be glad you got another 30 points. And then you can probably go through this a little faster, but if things break down, you might have to start from the beginning and try it again to see what went wrong. So I'm going to go through this a little faster. 51. 1 more click. Now the control signals are on for state 51. Click again. 52. Control signals are on. Notice my PC counter got incremented. Notice my instruction 5000 is on bus 3, ready to get clicked into the IR. 53 on. Now we got our instruction there. And we can go ahead and there's 5. That's the OR immediate instruction. And click again. And that turns on the control signals. Now we go up here. This is where we actually execute the instruction, state 66. 1 more click. We turn on the control signals for state 66, and this is where you want to, again, go check all of your clocks and your decoder or your tri-state buffers. Is register 0 going on to bus 1? Yes. Is register 0 the one getting clocked? Yes. Is our unsigned immediate going on to bus 2? Yes. Are we getting the 0 out on here? Yes. So that's the state to really check. Clock it again. Turn on the control signals for that state. Did register 0 stay 0? Yes, that's what my simulator did. And so now we keep doing that. I'll run the next instruction. I'm not going to show this on the video, but I'll show it this way on the video. Can't quite see my full screen, but you can see the next instruction is a load high immediate into register 1. Again, nothing changes. One more step. Now we get our first change. Register 1 has 5. That'll be it. We'll run another 2 instructions. I'll run it to this point so you can see that the 5 gets caught into that register. And also know that our program counter should be on 3. When it's 3, we're going to do the OR high immediate, but remember that the program counter is already incremented to the next instruction. So it's really when it's 4, this instruction is happening. Okay, so we'll fetch the next instruction out. This is the load high immediate instruction. I'm going to do that one fairly quickly. And turn on the control signals for 68. That's where everything's happening. Make sure we're dealing with register 1. Make sure that that stays at 0 on this next state. Click. Yes, good. Okay, let's fetch that OR high immediate instruction out. This is when our PC counter is 3. But our PC counter is going to get incremented to 4 before we execute the instruction on at memory location 3. So one more time. Now we've got the OR high immediate again. And 66, we're there. One more click to turn on the control signals for that. And we should see, yes, we're getting that 5 out onto bus 2. It's getting passed through onto bus 3. So again, this might be the state where you want to check all the clocks and tri-state buffers on your registers. Make sure, I believe that's register 1. Yes, a low voltage there. Yes, a low voltage there. And we got the unsigned immediate going on. That's where we really want to check. One more click. And go over, turn on the control signals for state 67. Yes, we got 5 onto register 1. And then we can click again and do the next instruction. So go back to your simulator, run the next instruction, see what it did to your registers, come to this, run the instruction, make sure it matched. And let's say that you notice that at one step you see a bunch of red coming through. What you want to do is you want to run it right to the point where the red first shows up. And then you can drill down into circuits like our ALU circuit right here. We can, if you have your pointer tool or this little finger tool, you can click a circuit once and it kind of circles it and you have a magnifying glass. Then double click it and you can go into here and you can see where is that red coming from. Now you want to trace it back from bus 3. The red might be coming out on bus 3 somewhere, and you can trace it back and find out where the red is coming from. You might have to go into your ALU bit, maybe even further into your adder and your mux to make sure everything is working right. And then to get back out, just click back onto your data path circuit. And now you're back out ready to do that. So you might have to go drill down in and fix it. Now, by the way, if you have an error in your ALU bit, you just need to fix one of them. You don't have to fix all 16. The same thing with your adder and your mux. So good luck with that debugging process. It is slow. Just know that you might have to spend a couple hours slowly ticking that clock. And if you run out of time or get frustrated, remember there's always partial credit. So good luck, and hopefully we get lots of working CPUs. Now just another couple of tips on debugging. Sometimes the red shows up a little bit later, so if you look at take a note of your PC counter on when that red shows up, and maybe go through the instruction right before that really slowly. Drill down, look at your control signals, see if any red starts showing up. And another thing, the other instruction, a couple of gotchas that might help are your branching instructions. If you're getting the answer button, it's not the right answer. You might want to check to make sure that you've hooked up your 0 and sign bit correctly. If those aren't hooked up correctly, you might not do the branch like you're supposed to do it. So pay attention to those branching instructions. Two things can happen. One, you just do the loop one time and you don't do it as many times as you're supposed to. Another thing, you might get caught in an infinite loop and never finish the loop because you always take the branch no matter what. So, and another thing that might help you debug is you can debug using the loop that using my program you can debug, because I just showed you in the video exactly what should be happening. That might help you debug. But when you pass off, you got to use your own program. Show your own program running in the simulator. Show the output, and then show that your CPU can run that same program as well. Make a screencast of that. It doesn't have to be terribly long, and if your CPU is super slow, it might be a little bit long. Usually I think Java version 8 doesn't run too fast. If you have Java, version 13 or something, it runs quite a bit faster. So once again, good luck.